Today we'll learn the overview of a mechanical ventilator, how it works, what are the functions, how do we regulate the function of a ventilator to suit the need of a newborn baby. So here we'll learn the overview of a ventilator, the hardware, that is a visible part of a ventilator, the software integrates the working of the hardware and helps us to know the function of the ventilator. Then we need to learn about humidification. So basically in this, we will learn the hardware, the software, and the humidification, that are the basic needs of any ventilator. The objectives of a ventilator are to deliver pressures. We have two types of pressures delivered to the babies: an inspiratory pressure called PIP and an expiratory pressure called PEEP. The inspiratory pressure is delivered to the lungs for a time called TI, and the expiratory pressure, that is PEEP, is delivered for the time TE. So apart from the pressures, the ventilator also delivers oxygen, and the concentration of oxygen is delivered is measured in FiO2. So for delivering oxygen in a concentrated gradient, you need compressed air source, compressed oxygen source, and a blender to mix these two, air and oxygen, to get the delivered FiO2. Then whatever gases we are using that are coming from the ventilator are cold and dry. So we have to warm and humidify these gases before they go into the airway. So the three basic functions of a ventilator are to deliver pressure, to deliver oxygen in a concentrated gradient, and to warm and humidify the gases. A ventilator also helps a physician for appropriate delivery of these pressures, oxygens, and it guides the physicians in adjusting the settings to suit the needs of the baby. So the ventilator also has flow sensors, graphic displays, and measures the respiratory mechanics to ensure that the pressure and oxygen are delivered appropriately to the needs of the baby. So coming to the hardware, so what do we need to deliver pressure? So we need to deliver pressure, we need flow of gases in a closed circuit, and we need something to regulate these pressures, and that is a pressure valve. So for generation of pressure, we need a flow of gases in a closed circuit and an expiratory valve or a pressure valve. We also need a pressure sensor for measurement of pressures that are being delivered to the baby so that this can be regulated. Then we need compressed air, compressed oxygen, a blender to titrate the FiO2, and also to measure whether the blending is appropriate or not using FiO2 sensors. Then we need a closed circuit that ensures that the gas flows in the circuit from the ventilator back to the ventilator, and it has a limb to connect to the patient lungs. Then you also have the flow sensors, which are sitting between the circuit and the patient, which are used mainly for measurement of pressures, flow of gases going to the patient, and volume of gases which is going to the patient and coming from the patients. So these flow sensors are very useful for synchronizations, for volume targeting, and also for graphic displays. The flow sensors are the important components of ventilators, which are used to set the modes, and the mode setting is basically based on how do you titrate or how do you trigger the ventilation, and how do you terminate the inspiration. So the details of this hardware we'll learn in the subsequent slides. So the hardware includes flow of gas and a valve assembly, a pressure sensor, compressed air, compressed oxygen, blender, FiO2 monitors or FiO2 sensors, a closed circuit, and flow sensors for measuring pressures, volumes, and flows. So this makes up the hardware of a ventilator. Now coming to the software of a ventilator, the software receives the signals from the hardwares and either displays those settings and also helps us in titrating the settings as based on the needs of those babies. The softwares helps in titrating pressures, volumes, and compared to what is delivered to the patient. And the measurements are the measured pressures and volumes are sensed by the flow sensors. These are the feedback goes to the machine and the machine titrates the pressures and volumes so that the desired volumes and pressures are delivered to the patient. So it is also the software also is used mainly the flow sensor. It picks up the patient efforts and helps in triggering the inspiration. It helps the machine when the inspiratory breath or when the PIP has to be delivered to the patient. Software analyzes the flows and the volumes going to the patients. So because it analyzes the flows, it also helps the machine to understand when it should stop the inspiration and when it should terminate the inspiration, that is a pressure delivery, that is a PIP pressure or the volume delivery to the patients. So the software also integrates itself so that if you set the alarms and the limits, the machine will tell you that, okay, the baby is receiving inadequate pressures or volume, or it is receiving excess pressures or volumes. It also has a graphic display of the measured pressures, measured volumes, the respiratory mechanics, and this helps us, the physicians, in analyzing what exactly is happening to the baby's lungs and how we change or titrate the ventilator settings. Now, if you look at the pressure generation in any ventilator is based on the simpler principle called IRS-TPs. So IRS-TPs is a T where there is gas flow flowing from one end to the other end. So, and this T is communicated to the patient lungs. So when the gas is flowing across the IRS-TPs, no pressure is retained in the tube and no flow goes to the patients. Now, when you obstruct the flow of gases in the IRS-TPs, as you can see here, on one end is occluded. So the gas which is flowing in the tube will start going across into the patient lungs. So if you connect the patient lungs to the T, you will see that the gas, when the gas is flowing in the tube, and if you occlude one end of the tube, the gas will go to the patients. And this is what basically done in a ventilator. In a ventilator, you have a gas flowing in a circuit. You have a patient lung which is attached to the circuit. And if you occlude the flow of gas in the circuit, part of that gas will go to the patients. And again, we'll look at the details of this in subsequent slide. So this is how a ventilator design is. So you have the ventilator gets input air and input oxygen. These are compressed air and compressed oxygen, which is delivered into the machine at 50 pounds per square inch. And inside, so these air and oxygen reach a chamber where air and oxygen are mixed proportionately to get to the desired FiO2. So you have a blender which allows the air and oxygen to reach this high pressure chamber at the appropriate proportions to get to the desired FiO2. So the blender decides how much of air and oxygen to come into this high pressure chamber. From the high pressure chamber, the gas flows into the low pressure chamber. And from the low pressure chamber, the gas flows into the circuits. So you have from the ventilator, the gas is flowing into the circuit. That is a red arrow. You can see it is going into the circuit. And it flows across the circuit back to the ventilator. So the blue circle indicates that is the expiratory port of the ventilator, and the red circle indicates the inspiratory port of the ventilator. So the inspiratory port, the flows goes into the inspiratory circuit, and you have a gray arrow there, which is actually connected to the patient lung. So from the red circle to the gray arrow, it is an inspiratory circuit, and from the gray arrow back to the blue circle, it is the expiratory circuit. So that normally the gas from the ventilator flows across the baby across the patient back into the expiratory port. So there is a continuous flow of gas in this circuit. And at the end, when the expiratory circuit goes back to the ventilator, you have an expiratory wall, and the expiratory wall here is depicted with the blue circle. So there is a gas flow in the circuit, and this gas flow is obstructed by this blue circle. Thereby, the pressures are built in the circuit. And when the pressures are built in the circuit, part of the gas will go into the patient lungs, which is connected to the Y arrow, which is connected to the gray arrow. So basically, a ventilator has an input compressed air, compressed oxygen, a blender, high pressure chamber, low pressure chamber, a flow regulator to ensure that adequate flow goes into the circuit, and an expiratory valve which will obstruct the flow of gases. And you have a patient connection which is in between the inspiratory and expiratory circuits. So the TPs and the endotracheal tube are connected across this inspiratory and expiratory circuits. So when the gas is flowing from the inspiratory to the expiratory limb, so the flow in a ventilator gas flow is constant. The gas will continues to flow from inspiration from the inspiratory limb to the expiratory limb. So the expiratory port, it is where the expiratory port is shown here, that when you have the expiratory port here, it obstructs the gas flow. And when it obstructs the gas flow, so now we say that there is some obstruction, the gas will start flowing into the patient. And when you increase the level of obstruction, that is a PAP, then more gas will flow into the patient till the pressure in the lungs equalize to the pressure in the circuit, and excess gas will move to the atmosphere. So basically what we are doing is to ensure that you have different pressures in the circuit, you are using differential expiratory obstructions. For PEEP, you give minimal obstruction, and for PAP, you keep on increasing the obstruction, but the gas flow in the circuit is constant. When you obstruct the gas flows, you will get pressure in the circuit, and that will help in flowing of gases into the patient lungs. So here you can see here that you have the ventilator, you have the inspiratory limb, you have the patient lung, you have the expiratory limb, and the expiratory valve assembly. Now let's see how this works here. So the inspiratory limb, the expiratory limb, the gas is flowing in the circuit. The gas is flowing into the circuit. So there is no obstruction, so there is no pressure built in the circuit. Now we created some obstruction to the gas flow. Now there is some pressure built up in the circuit. A pressure of 4 is built up in the circuit because you have obstructed the gas flow at the expiratory port. Now since the pressure in the circuit is 4 and the pressure is lung is 0, some gas will start flowing into the lungs. The lungs will inflate, come to the FRC and inflate till the pressure in the lungs become 4. Once the pressure in the lungs becomes 4, no gas flow from the circuit to the patient happens. But the flow of gas in the circuit is continuous. Now the pressure in the circuit is set at 4 and the pressure in the lung is 4. So no flow is occurring from the circuit to the patient. Now we'll increase the level of obstruction. So we increase the level of obstruction. Now, when we increase the level of obstruction, the gas flow is constant. The pressure in the circuit rises. So from 4, it has come to 20. So this is something like a PAP pressure. Since the pressure in the circuit is high, the gas will continue to flow into the lungs. The lungs will expand. The pressure in the lung becomes 20. Now, when the pressure in the lung is equivalent to the pressure in the circuit, gas flow the gas flow in the ET tube, or the connection between the circuit and ET tube, no gas flow happens. Now this gas flow is 0 in the ET tube, but the gas is flowing continuously in the circuit. So as long as the expiratory valve or as long as the expiratory port is closed to give that pressure of 20, the 20 pressure will be maintained in the circuit and in the lung. Now when the obstruction to the gas flow decreases, that is from the PIP obstruction, it comes to PEEP obstruction. The pressure in the circuit drops down. So from 20, it has dropped down to 4. Now the pressure in the lung is high. So the gas will start flowing from the lungs to the circuit, and the pressure till the pressure in the lungs become 4. So the lung deflates. And then the pressure in the lung also becomes 4. So now once the pressure in the lung and the circuit is 4 each, no gas is flowing in the endotracheal tube, but the gas flow in the ventilator, in the inspirator limb and expirator limb is continuous. So I hope you understand how a ventilator works. So there is a continuous gas flow. There is an obstruction to create PEEP pressure. There is an obstruction to create the PIP pressure. And during PEEP pressure, the lung inflates to get to the FRC. And during the PAP pressure, the lung inflates further for giving the tidal volume. And the titration between the PIP and PEEP continues as long as you give the ventilator breaths. The PIP obstruction will continue for the TI time. The PEEP obstruction will continue for the TE time. And that will give you the rate. So depending upon how long the TI is there and how long the TE is there, the rate is decided. So you inflate and deflate the lung. When you deflate, the lung is deflated only to the PEEP or the FRC. So you can see here that in this ventilator, you can see here, there is a inspirator limb, the humidifier. From the humidifier, the gas is flowing to the patient lungs. And from the patient lung, there is an expirator limb, which is going back to the ventilator. At the junction of the expirator limb and the patient and the ventilator, there is an expirator valve assembly, and this is highlighted here. This is the valve assembly which will regulate the PIP and P pressures for the inspiratory and expiratory time. So you set the pressures and the pressure sensors. So you have the pressure sensors which are measuring the pressures inside the flow sensors and exactly telling us that whether these pressures which are sensed are actually to the set pressures or not. And if the delivered pressures are less than the set pressures, then the expiratory valve assembly will titrate accordingly to deliver the desired pressures. So now we understand how the pressures are regulated in a ventilator. So the obstruction to the gas flow, although we have shown is a mechanical obstruction, it can be different type of obstruction like a solenoid valve or a diaphragm or a reverse flow. So there are different methods of creating obstruction to the gas flow, and depending on the method of obstruction, the ventilators will differ. Now coming to the second component of delivering oxygen, oxygen is delivered in concentrations called FiO2 or in proportions called FiO2 or fraction of inspired oxygen. And for that, you need a compressed air source, compressed oxygen source. Then you need a good blender to mix air and oxygen. Based on the FiO2 which you set, the oxygen and air, proportion of air and oxygen coming into the ventilator will vary. And you have a FiO2. So if you set 50% here or 60% here, the gas coming into the high pressure chamber will be having 60% oxygen because the blender will allow air and oxygen proportionately to get to the desired FiO2. So after the mixture chamber, you have an FiO2 cell, which is actually measuring the FiO2 in this chamber. And this FiO2 will display the amount of gas, the concentration of gas, which is coming into the inspirator limb. So the gas concentration in the inspirator limb is measured by FiO2 cell, and the titration of air and oxygen mixing to get to the desired FiO2 or the set FiO2 is, we set the FiO2 on the blender and you see whether that set FiO2 is delivered or not using an FiO2 cell. So FiO2 cell tells us the concentration of oxygen coming to the lungs, coming to the circuit, whereas the blender will help us in titrating the input air and oxygen to get to the desired or set FiO2. So the ventilation circuit is a closed circuit. There should not be any leaks because the concept is the flow is happening in the circuit, which is a closed circuit, and you're obstructing the flows to get to the pressures. So normally, if you see the ventilator circuits, they are corrugated. They're corrugated to give a memory and to prevent the kinking of the circuit. And inside the circuit are stiff so that there is no major compliance of the lung. And so that stiffness gives low compliance and the corrugation gives avoids kinking of the circuit. Now let us look at the software of a ventilator. The software of a ventilator is nothing but a pressure sensor or a flow sensor. And so there is a chip inside the ventilator which gets the feedback from the flow sensors. The flow sensors are both pressure sensors and flow sensors. And these measurements which are coming from the patient are displayed on the machine and using, so you have a display on the machine and you have a processing chip inside the machine. The chip processing and the sensor called flows software of the ventilators. The software helps us to display the set parameters, the measured parameters, and also gives a graphic display of the set and measured parameters. Also, the respiratory dynamics can be displayed on the ventilator using the software. Software also analyzes the respiratory mechanisms like compliance, resistance, leaks, C20 by C. So all these are done by the software. So the ventilator software, you can see here, you have a screen here, and on the bottom, you can see, you can set the modes here. So this is how the modes are based on the mode which you set, the software will regulate the settings accordingly. Then you have, if you select a mode, above that you will have to set what parameters in that mode you have to set. So you have the modes, the panel where you can set the modes. You have a panel based on the mode which you select, you have to select the settings. So the ventilatory settings are, these are the ventilatory settings you will titrate for each baby based on the lung condition. Then you have a panel on the right, which is actually telling you how much actually is going to the patient in a digital format. So here you can see here, you have set 15 by 4, and you can see how much PIP is going is 15, PEEP going is 4, and the mean pressure is 5.7. So what is set here is on the horizontal panel. What the baby is getting is on the vertical panel. And you can also see the leaks, you can see the tidal volumes, you can see the baby's breath rate. And so what you set a rate are on the horizontal panel, what the baby's breath rate is measured on the vertical panel here. So whatever is displayed here or whatever is going to the patient here are the reflections of the flow sensors. The flow sensors measures and displays on this vertical panel. And how the machine is regulating is based on the input which you give on this horizontal panel. And you also have a graphic display, which is helping us to know whether we need to make any adjustment in the ventilator settings, whether there are any leaks, whether there is any auto PEEP going on, or whether there is air trapping going on, whether your settings of PEEP, PEEP and TI are all right or not. So all this you can analyze from the graphic display of the machine, which is the software of a machine. So inside the machine, there is a chip which gets the feedback out. So which gets the feedback from your set parameters, and also the feedback from the set parameters goes to the chip, and chip will regulate the expiratory valve. So will regulate the expiratory valve based on the settings which you have given in this horizontal panel. And what actually is going to the patient is measured by the flow sensor. And this feedback from the flow sensor also goes back to the chip and also goes to the display panel. And whatever is going to the patient is displayed on the vertical panel and on the graphic panel. And based on whatever is going, and if it's not matching with the set parameters on the horizontal panel, then the regulation will happen on the expiratory valve with the help of the chip, which is sitting inside the ventilator. So the software components are mainly the measurements through the flow sensors or the pressure sensors and the chip sitting inside the ventilator. So these software helps us to set the modes, because the modes are nothing but when you are starting inspiration and when you are starting expiration. When you are making the gas flow in the circuit to go to the patient, when the starting of the flow from the circuit to the patient is called triggering, and when the flow from the circuit stops to the patient is the expiratory synchrony or termination sensitivity. So based on the flows which are happening from the circuit to the patient, you can decide when you can trigger the inspiratory breath and when you can stop the inspiratory breath. So based on when you are starting inspiratory breath or the flows into the patient, and when you are stopping the flows into the patient, you have different modes of ventilation like SIMV, assist control, and PSV modes of ventilation. Flow sensor also helps us in measuring the tidal volume, the minute volumes, the inspiratory flows, expiratory flows, leaks, compliance, resistance, and all other respiratory mechanics. It also helps you to measure the pressures which are in the circuit and also in the patient lungs through the endotracheal tube. So the software regulates the pressures which you deliver to the patient, that is PIP, PEEP, TI, and TE. So based on the settings, and this regulation happens by titrating the expiratory valve for the desired timings of TI and TE and for the desired proportions of obstruction using the PIP and PEEP obstructions. So the software also regulates when the flow from the circuit to the patient should start and when the flow from the circuit to the patient should stop. So that is inspiratory synchrony is called triggering, and when the flow stops is called termination sensitivity. So third component of a ventilator is the humidification. So humidification is one very important component of neonatal ventilation because the gases which are coming from the compressed air sources or compressed air and oxygen are cold and dry. So these gases which are coming into the inspiratory limbs are warmed and humidified in the inspiratory in the humidifier chamber, and they continue to be warm and humidified in the inspiratory limb using the heater wire, so that at the end when the gas goes to the patient at the TPs, the gas is delivered at 37 degrees with 100% relative humidity. So this is called active humidification, and active humidification is must for all neonatal ventilations. So these humidifier works in such a way that when the gas is coming to the humidifier and when it is exiting the humidifier, it comes at 37 degrees with 100% relative humidity. And in the inspiratory limb, the gas continues to get heated till reaches 40 degrees. So the relative humidity will drop around 80% in the inspiratory limb and till the heating element is there. From there till it reaches to the patient, again, it will come back to 37 degrees with 100% relative humidity. So the gas going into the nose or into the endotracheal tube is always at 37 with 100% relative humidity. So just to summarize, so ventilation means delivering pressures, PIP, PEEP for the required times of TI and TE, delivering oxygen, air in the proportions called FiO2, and delivering at 37 degrees with 100% relative humidity using a good humidifier. So for these, all the ventilators have the hardwares, which has compressed air, compressed oxygen, blender, FiO2 sensor, flow meter, a closed circuit, and an expiratory valve. Then you have the software, which is the flow sensor and also the chip inside the ventilator. And these regulate the expiratory valve to deliver the appropriate pressures and volumes and for the appropriate time. The software also helps us to set the modes based on when the gas from the circuit should go to the patient and when the flow of gas from the circuit to the patient should stop. So inspiratory triggering and termination of inspiration called termination sensitivity is also regulated by the software based on the modes which you set for the baby. So if you set an alarm, suppose you're giving a PIP of 14 and the baby is getting a PIP of 17. So the ventilator will tell you that you have reached more than the set pressure or more. If you're setting based on your setting and the delivered pressures and wall not matching, you can set the alarms, and that alarms will be highlighting the physician to take a corrective action. So the third component of the humidification, the purpose of humidification is to deliver the gas at 37 degrees and 100% relative to the nares or to the endotracheal tube in a ventilator. So thank you one and all for the patient listening, and I hope you understood a basic mechanical ventilation ventilator purpose for a newborn ventilation. Thank you.